We are joined today by Ms. Goda Ramkumar, Vice President of Data Science at Swiggy, focusing on driver, delivery, maps and supply chain space. Prior to this, she was General Manager Data Science at X to 10X, establishing data science journey and practice in the startup ecosystem. Previously, she was at Ola for 2 years as Principal Data Scientist, where she led the machine learning and optimization algorithms behind pricing and matching. She worked at Sabre for 10 years before Ola on a variety of problems in airline pricing and venue management. She holds an undergraduate and master's degree from IIT Madras. She has several publications and presentations in industry journals and academic conferences. Today, she will share with us her own journey and career in operation research and analytics. She will be covering examples of optimization problems being solved across the airline industry, mobility, quick commerce, and marketplace systems in general. Let us extend a warm welcome to Ms. Goda Ramkumar.
Okay. Good afternoon, everyone. It is to be back at a campus. It kind of took me back. By the way, I'm from IIT Madras. So it took me back to those days. And I was just retrospecting as, people were talking about the different areas of work happening here. One of the reasons I'm here is also because I took up that minor that was offered to undergraduate students. And I fell in love with it. My major was actually in biotechnology. But OR became my first love, and then I decided that this is the area I want to work in. Right? And then I took up the job, and today I thought it will be good for me to just walk down the memory lane and talk through different problems I saw across the companies I worked with, which made me only fall in love with OR more and more, right? So I hope it will be interesting for all of you as well. First, I would like to start with, because I started with OR and today I'm leading data science, so just the definition of data science itself has changed over time for me. I've come up with a very simple definition of it so that all the different terms we use are not confusing. It's just making data useful for the business, right? The different data science teams across the companies. Now that means you have to collect the right data, you have to engineer it and architect it the right way, create platforms so that the data is just accessible and discoverable. It also means you have to generate analytical insights so that you can drive some decisions out of data. That does not mean a machine or a system has to make it, people have to make decisions. Then comes you have to be able to think about the data products. By data products, I mean it could be products that make insights easily available to you. It could be products that are making decisions based on data. That means in the background, a lot of machine learning, optimization, all of it will be running. And none of it is taken at face value, which means a lot of experimentation and being able to analyze experience. So you go back to stats, right? So it's a culmination of different fields that has come together and just got a term, right? So with that definition, I'll start with the very first company I worked with, which was Sabre. This was in the airline domain. So when we think of airlines, what is the optimization problem that they have to solve? I think this is one of the traditional and the oldest industries where probably OR started getting applied. So when we think about it, there are a bunch of business problems, right from when you think, what is the schedule that I have to put out there, right, in terms of planning your network, putting the schedule. Then you think of how do I price it. This is the area I worked with most when I was at Sabre, pricing and revenue management. Then of course you schedule the flights and you have to package it nicely and extract as much ancillary revenue as possible from people, right from seat to baggage to meal to everything. Then you have to manage the operations and things go wrong, which means you have to recover from it. So each of these problems, if you think about it, has an optimization or OR application running at the back of it. Now, all these OR solutions that we think about, every decision that has to be made here has to be powered with information. Now, when we think about information, it can come from just data processing, it can come from machine learning models, deep learning models. One of the reasons I'm very happy that IEOR is becoming a department and having an undergraduate program is that a lot of these days the trend is that we have generative AI, we have large language models, everyone wants to work on deep learning, big models. All of that are predicting something, right? Ultimately, someone has to make a decision based on that. And without OR, how will you make those decisions, right? So it's very tough to find people with the appreciation for that, and I'm sure this program will generate more of such people and make it easier for us to solve these problems. Then, of course, I put a lot of animations. Apologize for that. So I'll just talk a little bit about the revenue management problem that I spoke about. The problem is simple. It's economics. You have to match demand and supply. If you set one price, you'll just cover a small part of the area of the possible revenue you can make. If you do revenue management using a big math optimization problem like this, it's just a linear programming problem, by the way. I thought I'm coming to an academic institution, so I should also sound a bit technical. So we solve a linear programming problem and try to decide what are the price points to set. You divide a aircraft into multiple classes, and each of the class will have a price point, and all you're deciding is at every point which class is made available to the customer, right? When we say it like that, it sounds simple, but if you imagine a network of an airline, there are multiple flights, multiple people connecting from location A to location B. Not all the people on the same flight want to go to the same place. So just the dimensionality and the scale is so huge that it makes it a challenging and interesting problem to solve for. So you can apply a simple linear programming, but when it becomes a very big origin and destination carrier, all you have to solve is the dual of the linear programming problem and come up with the minimum price of every seat, and then you can sell any market on that flight. If you have a point-to-point carrier like we have Indigo in India, then you are just trying to solve a multi-stage decision problem there, like dynamic programming, where at every seat, I'm trying to decide what's the price I want to set on every seat on my flight. So that's just a glimpse of how in airline industry we solve this problem. Then I'll go into mobility, which is I almost crash landed from air transportation to ground transportation when I joined Ola. And why I say crash landing is because from a big global company to a startup ecosystem, where suddenly 300 days that we had to solve an optimization problem became 300 milliseconds. So the same problem kind of translated to something very real time, very on demand, and very large scale that you have to solve for. Multiple optimization problems like how do you plan the surges, surge pricing, which most of you would have faced as a customer. How do you match the pooled rides? This is one problem I'll deep dive into, which is like when you're sharing cabs, multiple people share the same cabs, how do you match them efficiently? How do you match the driver with the rider? How do you design the incentives so that you have enough supply on ground? How do you plan the supply? Multiple optimization problems. The pool ride matching problem was a very interesting one because there is somebody already traveling on the cab. There are multiple people who are requesting for a cab ride, and in real time you have to come up with which is the right combination. There itself it kind of becomes a NP-hard kind of problem. The nice hack there was you can pre-compute many of those. By pre-compute, what I mean is there are a lot of people in the ride. There are a lot of new requests that are coming in. And now, if you think of it, it's like a graph. Now you're trying to match and try to find cliques in this graph, which match very well. And the score could be based on how much overlap they have on their ride. Is it economical, like is it profitable to send them on the same ride? How much deviation the customers will face? What is the ETA we have promised? It becomes a clique detection problem, which can be pre-computed. And in real time, you're just doing a very greedy scoring, right? So this was one way to bring down, like solve the large scale problem where You're doing most of the rigorous part before, but in real time, you're trying to solve a much simpler problem. Then I come to quick commerce. I think COVID made a lot of things to be delivered at home, and in 10 minutes, in 8 minutes, that number is just reducing day by day. I think it has also changed the habit of people where you start cooking and then you realize something is not there and you start ordering. So in this, the very first problem is the network design. I think, sir, just before this was talking a lot about facility location, right? That's the primary problem you have to solve. If you have to really cover all the customer demand that you have to see how the competition is, because the demand gets split. Where are the competitor locations? Where do you have to place your stores? And the cost structure, of course. Is there enough demand density so that you can be profitable? So network design is a primary problem in quick commerce space. Then, of course, once you order, the delivery partner needs to be assigned to the order. This is like a bipartite matching problem that we solve for. But imagine the scale here, right? The number of orders, the number of drivers, and all the possible combinations that can happen. And for each of these, you have to be able to predict so that you can score it well. Like, what is the time it's going to take? What is the time it's going to take to prepare the food? Multiple predictions, almost more than 1 million predictions in 1 second. And then you have to find the right combination to assign to. Then, of course, the supply planning, which is the staff planning problem. For every delivery partner to come there at a particular time, they need to have a schedule. They need to have a slot where I'll work in, right? How do you plan these slots so that you can trace the demand curve as closely as possible? It's an optimization problem, but luckily more batch problem that you have to solve for. You don't have to solve for it in real time. Then, of course, scheduled delivery. A lot of us will order on big basket and wait for the next day. Sometimes in a particular slot, it has to be delivered. This is very efficient because you can batch multiple orders together and kind of condense them and send them together. But what that also means, it's a NP hard problem because so many combinations, a vehicle routing problem, right? So now, if we have to solve for this, of course, you have multiple objectives. It has to be minimum cost, and you have to deliver within the window you have promised to the customer. You have to make sure the delivery partner's side of experience is also handled. They are well utilized. Your fleet is well utilized. And of course, many constraints. What is the mode you're using? Is it a two-wheeler? Is it a three-wheeler? Is it a van? Different capacities, weight, volume, multiple constraints. So the way kind of we solved for it is we kind of broke it down into first solve for the last mile, then we'll solve for the first mile. By that, what I mean is, I don't really need to think about who the delivery partner who's going to deliver this is. First, let me try to find good candidates that can be clubbed together, right? So you solve a capacitated time windows vehicle routing problem to just optimize for the last mile overlap. Once you do that, then you take those like best candidates we have got and try to find the delivery partner in real time so that the first mile or the delivery partner is as close as possible to the first pickup, right? So by breaking this down, we could handle the scale of the problem that was required here. So the whole point of saying all this was just the trend or the transition this field is seeing day by day. One definite transition was more batch problems to very real-time, very on-demand, high-scale problems to solve for. That also and in terms of the information that's going into these optimization models, it's transitioning from a very traditional predictions we had, like time series algorithms. They are used even now, but it's also transitioning a lot towards getting these predictions from deep learning models, LSTM models. So the information system that is generating inputs into optimization is changing. And many companies need all the things, so it's not a single objective problem ever. It's always a multi-objective, multi-decision criteria problem you're solving for. That means how do you really trade off? What are the methods you come up with to guide the business? On that becomes very crucial. And also because it's more real-time and there is also an angle of explainability involved. Sometimes instead of going for very exact algorithms, you solve it via heuristics, which is more explainable and at the same time, intuitively, it's making sense to a lot of people. There might be that last juice of optimality you're leaving on the table, but explainability becomes much more important. Then, of course, what model gets chosen depends a lot on experimentation, which means a lot of focus on experimentation analysis, methods to normalize which are the organic factors, which are the inorganic factors, and how do I ensure the experiment design is in such a way that there is low interference, right? And of course, there are a bunch of commercial solvers like they were talking about, which are used, which means the problem that we as humans are solving is making sure we are formulating it right and we are modeling the problem right. And for the stochasticity, simulation-based solutions and running multiple simulations to choose the right robust method that you can go with. These are some of the things which I did not know when I graduated, but learned over time that these are the important aspects to apply OR in business is something I thought would share with all of you. So that was the brief talk I had. Thank you. Any questions? Any questions? No customer care questions of Swiggy. So.
What did you mean by organic and inorganic?
For example, let's say I'm trying to club 2 orders, and that's the optimization I'm solving for. That means I'm definitely going to make sure with the same capacity of delivery executives available, I am going to deliver more orders. So that's something I am changing because of the change I'm doing. Whereas let's say it rains. That's an inorganic change because you are making the change. But it rains and the speed comes down of the entire network. That is something you did not cause via the experiment. So that's an organic change that happened. So you have to separate out these and normalize for it so that you can compare, control, and test. Yeah.
Based on your experience, has it any time happened to you compose a solution which is just based on common sense, like in matchmaking and all that? There are mostly some common sense based solutions are there. Any time you have come across that, no, it was not a common sense based solution, or told me something different?
I think common sense based solutions have solved the problem 70-80% of the times, right? And it also gets 70-80% of the juice that's out there. But sometimes when your scale is high, taking that 80 to 81 also becomes important. And there, OR plays a huge role. Right. First solution is always common sense based. Yeah.
Scale in terms of customers or something.
You mentioned scale in one direction.
I think the scale that matters to at least the optimization problems that we solve for most is concurrent active customers. At the same time, how many active customers are shopping on your platform, right? Because every 1 minute, every 2 minutes, you're trying to solve a problem. So if you have millions of orders every day, like at least a couple of million every day, then there are certain peak periods where just the combinations that you have to solve for goes above, like I said, more than 4 million, 5 million combinations. Now, you have to break down the problem into pockets, but not lose the optimality. That becomes the most important problem to solve for. Yeah.
So you did not want customer-specific complaints to be raised in this talk, but where is customer in all this?
Customer, actually one of the values of Swiggy is customer comes first. So whenever we are thinking of a solution, in fact, we have to write a document in which you have to answer the question, how does that impact the customer, and negative, positive, both, so that we take a conscious call. Just to give an example, maybe not the optimization example, but let's say once you order, you see the track screen, and in that you show 14 minutes, 13 minutes, you're showing, right? As a data scientist, I can try to build a model which is trying to get every signal from the ground and react to it. My accuracy numbers will look great, right? But what am I serving for the customer, except that the number is going up, down, and then settling down. It's only increasing the blood pressure of the customer, nothing else, right? So keeping that in mind, you would rather choose a model that's more smooth and is giving most of the information and not trying to get accuracy every second, reacting to. Sometimes GPS signal does not come from the phone. You don't have to react to it unless it's a significant deviation. An example.
Any more questions?
Cool. Yeah, thank you. Thank you, folks.